In this video, we're going to be discussing the ratio test, which is one of the most useful tests for ascertaining whether an infinite series of real numbers converges. The ratio test grows out of the geometric series test, and we're going to spend a few minutes looking at a particular example before we formulate the ratio test formally. So here's an infinite series. The sum from 0 equals to infinity 4 times 2/3 to the n. So when n is 0, we have 4. When n is 1, we have 4 times 2/3. When n is 2, we have 4 times 2/3 squared. That's a squared plus so on and so forth. Now this is a geometric series. We can see that by looking at the fact that when we go from one term in the sum to the next, we are always multiplying by 2/3, which is less than 1, and the first term is 4. So this is a convergent geometric series. It converges to 4 over 1 minus 2/3, which reduces to be 12. Now, one way to see that a series is geometric is to recognize that when we go from one term in the sum to the next, we are always multiplying by the same number, r. We call r the common ratio. Another way to see that a series is geometric is to look at each term and divide it by the term preceding it. So if we take this term and divide it by that, we get 2/3. If we take this term and divide it by that, we get 2/3 as well. So instead of thinking about always multiplying by the same number, the quotients are always the same, the ratios, and that's why we call this the common ratio. Now let's say we modify this series just a little bit. So instead of 4 times 2/3 to the n, we have n times 2/3 to the n, summed from 0 to infinity. If you write down the first few terms in this series, you will see that this series is not geometric. You might want to just look at these first few terms and look at the ratios, and you'll ascertain that this is not a geometric series. Now here's a general idea about infinite series. Let's say I have an infinite series from 0 to infinity a sub n, a0 plus a1 plus so on and so forth. Now whether the series converges doesn't really depend upon the first, let's say, 100 terms. It really depends upon what's happening after that. So in general, whether a series converges all comes down to the behavior of the terms a sub n as n gets really, really large. And this idea is what's behind the ratio test. So a convergence of a series comes down to the behavior of a sub n as n gets really large. So let's go back to this series. The sum from n equals 0 to infinity n 2/3 to the n. We said that this is not geometric. Let's write down a few terms. So it's 0 plus 2/3 plus dot 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 dot. Now I'm going to write the 100th term, so that would be 100, 2/3 to the 100. I'll throw in the 101st term, and I'll throw in the 102nd term. Okay, plus obviously there'd be many terms after that. And what we're going to do is we're going to look at the ratio of this term divided by that term. We'll also look at the ratio of this term divided by that term and see what happens. Okay, so if I take the 102nd term divided by the 101 term, I see that I get cancellation of my exponents, so I get 102 over 101 times 2/3. And you know that's pretty close to 2/3, so I'll just put an approximately equal because this quantity is pretty close to 1. If I take the term corresponding to n equals 101 and divide it by the term before it, I get 101 over 100, 2/3 to the 101 over 2/3 to the 100. Again, this simplifies. I'll get 101 over 100 times 2/3, which is about 2/3. So, and this would keep happening as we go out further and further. So the upshot is that our series, while not geometric, when n is large, the terms are close to those that we would find in a geometric series with an r value, a common ratio of 2/3. Let me say that again. As we go out in the series far enough, the terms we'd see in this series, even though this series is not geometric, are indistinguishable almost from a series that is geometric. And so that's the idea behind the ratio test. So here it is formally. What we do is we look at the ratio of successive terms, the n plus 1 term over the nth term. We put absolute values in. We'll talk about that in just a moment. We take the limit as n goes to infinity, and we call that number L. Now, L, if it's less than 1, our series converges, and the series diverges when L is greater than 1. If L is equal to 1, the test is inconclusive. You need to try something else. This test is useful when the infinite series involves factorials or exponential functions, and we'll look at examples of both in just a moment. So there's some algebra involved with computing this ratio, computing this limit, and then we have to make a conclusion, form a conclusion based upon that. So let's go back to our example. N times 2/3 to the n. So the first thing we want to do is we want to write down what the nth term is. That's just n 2/3 to the n power. Now what we need to do is we need to write down the term a sub n plus 1. And the way we do that is we take this formula, and everywhere we see an n, we replace n with n plus 1. So I should be careful and put parentheses there. So that's the first step. Sometimes writing down what a sub n plus 1 is can be a little challenging. The next step of the ratio test is to take the absolute value of this term and divide it by the absolute value of that term. Now, in the examples we'll be discussing in the remainder of this video, the terms are always going to be positive to start with, so we really don't need to worry about the absolute values. That will come into play a little bit later on. So we take a sub n plus 1, which is this, and we divide it by a sub n. It is always at this stage where some algebra simplification is going to take place. We've got 2/3 to the n plus 1 in the numerator, and we have 2/3 to the n in the denominator, so there's going to be some cancellation. We'll have the limit as n goes to infinity, n plus 1 over n, and then there's going to be a 2/3 left right here. Now as n gets really, really large, this essentially becomes closer and closer to 1, as close to 1 as we like. So the limit as n goes to infinity of this is equal to 1. Now there's a more rigorous way, so to speak, of showing that, and that is to use L'Hopital's rule. Take the derivative of the numerator and the denominator separately, and then take the limit. But if you think in terms of rates and growth, which is fine, the dominant term in the numerator is n, the term in the denominator is n. In essence, this limit is 1, so our final limit is 2/3. So that's our L value, 2/3. And because that's less than 1, we know that our series converges by the ratio test. Let's do another example. The infinite series from n equals 1 to infinity, 3 to the n over n squared plus 2 to the n. Now this is not a geometric series. And that's a multiplication sign right there. So if I write a sub n down, I get 3 to the n over n squared times 2 to the n. Now if I take my formula and look at the n plus 1 term, that means I have to take this, and everywhere I see an n, I replace it with n plus 1. So I'll have 3 to the n plus 1. Substitute n plus 1 in there. I'll have n plus 1 squared times 2 to the n plus 1. Now what we have to do is we have to take this thing and divide it by this thing. So let's write down the n plus 1 term. That's what I have right here. Here's a little time-saving trick. A sub n itself is made up of a fraction. Dividing by a sub n, dividing by this, is the same as multiplying by the reciprocal of this. So instead of getting some long division mess, what we can do is take our a sub n plus 1 and multiply it by the reciprocal of this, which is n squared times 2 to the n over 3 to the n. Now there's going to be some simplification, some cancellation that takes place. 3 to the n plus 1, most of that will cancel with 3 to the n. There will be a 3 left. The 2 to the n plus 1, most of that will be canceled by 2 to the n, so there will be a 2 there. So we have the limit as n goes to infinity of 3 halves n squared over n plus 1 squared. Let's expand this. So we'll have the limit as n goes to infinity of 3 halves n squared over n squared plus 2n plus 1. Now, as n gets really, really large, the dominant term in the denominator is going to be n squared. So in essence, by looking at the n behavior, we can see that n over n squared we know is equal to 1. This limit will actually be 1 as n gets larger and larger. Another way to do it would be to use L'Hopital's rule. So the limit is 3 halves. That's our L value. That's greater than 1. So that says that our series diverges by the ratio test. An example with factorials. The ratio test is extremely useful when we're working with factorials. Now, just as a reminder, what the factorial means, the factorial of a natural number means you take that natural number and multiply it by it and the product of all its predecessors. So, for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. And one thing to notice here is that 5 factorial is the same as 5 times 4 factorial. Or in general, n plus 1 factorial is equal to n plus 1 times n factorial. And this is a really useful fact. So let's look at the series, the summation from n equals 0 to infinity, 3 to the n over n factorial. A sub n is 3 to the n over n factorial. My n plus 1 term I get by substituting n plus 1 in for n there. So I have 3 to the n plus 1 over n plus 1 factorial. Let's look at our ratios again. So a sub n plus 1 over a sub n. Again, the absolute values are not needed in these examples because the terms are all positive. So a sub n plus 1, I've written that down there. And I need to divide by a sub n, which is the same as inverting and multiplying. So I'll write that as n factorial over 3 to the n. Now we're going to see some cancellation right off the bat. All of 3 to the n will cancel with most of 3 to the n plus 1, so I'll have 3 in the numerator. Now we also know that n plus 1 factorial is the same as n plus 1 times n factorial. So all of this n factorial is going to cancel with all of that n factorial, so I'll have the limit as n goes to infinity of 3 over n plus 1. And that limit is obviously 0, which is our L value, which is less than 1. So our series converges by the ratio test in this example. Here are some examples for you to look at to do in preparation for class. The series from n equals 0 to infinity, n plus 1, 5/7 to the n. The series from n equals 0 to infinity, 4 to the n, over 2n quantity factorial. 2n quantity factorial. Now, here's a little hint to prevent an algebra mistake. It's pretty clear that this is what a sub n is, this much right here. To get a sub n plus 1, we have to take this formula, and wherever we see an n, we have to replace it by n plus 1. That means 4 to the n will become 4 to the n plus 1. Now 2n, we don't want to just multiply that 2 by n, we want to multiply it by all of n plus 1. So it's 2 times the quantity n plus 1 factorial. And here's a little, a little suggestion for how to simplify that 2 times n plus 1 factorial. So this is the same. If we multiply this, we get 2n plus 2 factorial. Now 2n plus 2 factorial is the same as 2n plus 2 times the number immediately before it, which would be 2n plus 1. And that 2n plus 1 gets multiplied by the product of all the terms preceding it. So the quantity in the denominator here is going to be 2n plus 2 times 2n plus 1 times the quantity 2n, quantity 2n factorial. And so when you use the ratio test and do some simplifying, you're going to see some cancellation taking place. And you're going to be using this fact right here. So see what you can do with those in preparation for class.